last class, basically we have discussed about different types of your nozzles in the sense depending on the Mach number. Okay. Uh, mm, so let me share the screen first. Okay, is it visible?
Yes, sir, visible.
Okay. So basically these things we have discussed in the last class. If you recapitulate, uh, your isentropic flow through variable area duct. Okay, so now mathematical forms will be more discussed today, and we'll try to finish as much as possible the nozzle part. Okay, the design, nozzle design. So basically, today we'll start with the joining. Okay, so okay, so relationship between you can see the Mach number and area. Okay, so one mathematical relation we will try to now find out some explicit relation between Mach number that is a very well known dimensionless number and which is very important for design of any nozzle. It may be convergent nozzle, it may be convergent divergent nozzle, whatever. uh, this Mach number is very important, and the area is basically obviously varying. Okay, the duct is actually variable area duct, whatever we deal with. So if it is either it is a convergent or it is a convergent divergent, so the area is also varying. So there, if we are having some explicit relation between the area or area ratio, I should say, uh, mm, and with the Mach number, so that if I know the Mach number, I can obviously predict the areas. Okay, so here we know this thing that Mach number is what? Velocity of the flow divided by the sonic velocity. Okay, m is equals to u by c. This thing we know. So similarly, like in the last class, I have shown some of the mathematical forms. So don't mix up all the mathematical forms, because each and every derivation, whatever I am showing, small derivation it may be, but each and everything is different. Okay, we are getting some different equations. So that means different relationships, I should say. So here you can see if I take log EBS or ln in the both sides, I first you cross multiply this equation and then you just take log over here. Okay, so you can see next we'll obviously you differentiate du by u. On the left hand side I will get dc by c plus dm by m. Okay, so keep it as equation number one. Now, as I told in the last class that most of the cases we will consider that my flow is type of your isentropic flow. So obviously the equation of sonic velocity will be like this. Okay, obviously the equation of your sonic velocity will be your c is equals to under root gamma rt, isn't it? This one is clear. Why I'm writing c is equals to under root gamma rt?
Yes, sir.
Okay, because this is just after applying the condition of isentropic flow for any ideal gas, we are getting this equation. Okay, yes, I have shown this equation how we are getting this. And next, similarly, we will take log now here also. So lnc is equals to half. Actually, is coming from this root. Okay, the power will be obviously in the front side. So half ln gamma plus half ln r plus half ln t. Now again we will differentiate. If I differentiate, you see the gamma and r are constant, so these two terms will be getting 0. So dc by c is equals to my half of dt by t. Now this will be obviously used over here, because here we are having one dc by c that you can see. Okay, in this first equation. So this is equation number 2 you can give. Now from equation number 1, what I can write, keeping this in this equation, just we can write, just we are replacing basically du by u is equals to half dt by t plus dm by m. Okay, very simple mathematics, just we are replacing and keep it as your equation number 3. Now we will use the basic energy equation. Basically energy equation is this term will be constant. We have earlier also we have seen that h is enthalpy, specific enthalpy, u is the velocity, And if we neglect the changes in the potential energy, then we can write this, that h plus u square by 2 is equals to constant for any particular section, obviously. Now, similarly, the same thing, same mathematical operation I will be giving over here, that dh plus u du, because 2u du I will get over here and 2 will cancel out. Okay, numerator and denominator, 2 will cancel out. So dh plus u du is equals to your 0. Fine. Now dh is equals to what? Cp dt. From thermodynamics, we know this. dh is equals to change in specific enthalpy. dh is equals to by Cp into dt, and u du is as it is. Cp is equals to your gamma r by gamma minus 1. How can I get this? Who can tell me? How Cp? How I am writing Cp is equals to this gamma r by gamma minus 1? Who can tell me? Hello.
The last day you told two
Yes.
equations Cp
What I
minus
told.
Cv, Cp minus Cv is equal to R and Cp by Cv is equal to gamma.
Cp by Cv is equals to gamma and Cp minus Cv is equals to R. Yes, very good. That we have to combine. Okay, we have to combine, and you can get expression of Cp also, expression of Cv also from this from those two equations. Just we are writing in that fashion. Very good. And also we are dividing by u square. You can see this. Okay, u square we are dividing on both the terms, and this side also. Here I am having 0, so doesn't matter. So what is happening on the right hand side? So dt by u square, here also u du by u square. Why I am doing this? Why I am doing this divide by u square? Anyone can tell me? Any idea? What I am trying to do?
So
Why I am
you want to try to replace that du by u value with
Yes,
that
very good,
equation.
very good. Du by u. Here I am having du by u. So that term I need. If I need, that's why I am dividing by u square. So these things are basically very common. Okay. So for any mathematical operation, better you memorize these things rather than you memorize the each and every step. Okay. So you just memorize the trick so that any derivation will be very small to you. So this, if I replace, okay, this u square also we know that u square here also, u square is equals to what? M square c square. You know that from this very first equation I can say that u square is equals to your m square c square. C square is equals to your gamma t. You can see that from here. Okay, c square is equals to gamma t. So m square gamma t. That is my u square, and this will be your du by u. So here dt by t, I'm basically here also I'm having dt by t, du by v is already over there. I can take common. Okay. So dt by t, if I here I'm having t also, here I'm having dt. So dt by t, if I segregate from this term, so obviously I have to take on the right hand side and I will get a minus sign over here. So gamma minus 1, obviously this gamma will cancel out. You can see this gamma r and gamma r will cancel out. So it is getting simplified, and minus of gamma minus 1 into m square into du by u. This term I am getting after simplifying this. What I am trying to find out, dt by t. Now if I replace this dt by t, combining this 3 and 4, combining the equation 3 and this 4, what I can write? Just I will replace this dt by t over here. So there will be no t term, there will be only u term, and there will be only u term basically, du by u and dm by m. Okay, that you can see. So here this term is basically here already we are having du by u, that's why 1 plus. Okay, here we are having minus, we are taking that into left hand side. So 1 plus gamma minus 1 by 2, from where this 2 is coming, basically from this half. Okay, into m square into du by u is equals to your dm by m. Already we are having dm by m, so that dm by m. So here if I just take a ratio, that dA by a, dA by a will be what? M square minus 1. Okay, m square minus 1 dm by m, m square minus 1 dm by m divided by 1 plus gamma minus 1 by 2 into m square. Now from where I am writing this? From where I am writing this basically? This dA by a, who can tell me? I am trying to find out Mach number and area. Okay, Mach number, area, this Mach number I have got m square. Okay, so this is what? This part is m square minus 1 into dm by m divided by 1 plus gamma minus 1 by 2 into m square. Okay, from where I am writing this? From which equation I am writing this? Hmm? Any just that you have to recap a simple equation that you have several times used. Can you recapitulate this equation? Hmm? dA by A is equals to what? M square minus 1 into du by u or not? dA by A is equals to m square minus 1 into du by u.
Yes,
Am
sir.
I
This
audible?
equation.
So this is the equation. Okay, dA by A is equals to m square minus 1 into du by u. Several times we have used. Now you see here only think about du by u. So if I just take out this du by u from this equation, so it is nothing but dm by m divided by this term which is you're already inside the third bracket. So that is actually happening. Dm this m square minus 1 into du by u. So du by in place of du by u, I am writing dm by m. Let me show you. Uh, okay, up to this I have shown you. Okay, so how I am writing this? Basically, this dA by A is equals to m square minus 1 into du by u. Du by u is your dm by m divided by this third bracket term. So actually that we are having. So this is basically the explicit relation between Mach number and area. There is no other variable. If you see, gamma is constant. Okay, for a particular type of gas, my gamma is your constant. So because that is my Cp by Cv. So this is the explicit relation between the Mach number and your area. 5 marks question may come. Derive a relationship between for a particular isentropic flow. Derive a relationship between mathematical relation between Mach number and area. Okay, no other variable will be there. So in the last equation, whatever we have taken help, that equation is your basically dA by A is equals to m square minus 1 into du by u. Okay, so just you have to recapitulate this equation. Okay, so that you can get this equation. Is that clear? Any doubt regarding this derivation? Any doubt?
No, sir. No, sir.
Okay, thank you. So next topic that we will have, that is your sonic states. Very important. Now sonic states, from the name you can predict that sonic state means when my Mach number will be your 1. Okay, so sonic states means there may be different things at that means at any position in any particular flow of any duct. If I just achieve the sonic condition, then the properties at that particular section at that particular point of time, those states, actually those properties will be known as your sonic properties. Okay, so how we just denote this sonic properties? So when Mach number is equals to your 1, then the corresponding states of that system is called sonic state. Okay, like this U star, okay, U star, uh, P star, okay, rho star, and A star. So this star in the power we are having when we are having star, okay, that is basically we denote by the sonic state. Okay, so star suffix star, this A star means the sonic area, we should say. Okay, this sonic area is always, most of the cases it is my throat area. Okay, and at that position, at that point of time, whatever the velocity we are having, this will be my u star, pressure will be my p star, and density will be my rho star. It is just the notation. Okay, when Mach number is equals to 1, the states will be denoted by this. Now if I want to do some mathematical operation using these terms, basically we can write from the mass balance, or you can say from the mass continuity, you can write this, that rho a u is equals to rho star a star u star. Can I write this? Rho 1 a1 v1 is equals to rho 2 a2 v2. Very simple equation. Same thing I am applying. This rho a u is nothing but the product. This product is at any cross section at any position of the duct, but this rho star a star u star is for the sonic state. Okay, rho star a star u star is my for the sonic state. So here you see interest some typical your mathematical operation is there here. You can see I am taking the ratio basically a by a star. Okay. Often in the problem, okay, this equation, this a by a star, whatever the final equation I will derive, that equation will be used. So I have to find out the term this a by a star. Okay, a is the area at any section. A star is the sonic area or the throat area, I should say. Okay, throat area. So this is just by the ratio what I can write. It is equals to my rho star by rho into u star by u, just by simplification. Okay. Now u is
So, sir, can you explain that A star means what is sonic area?
sonic area means what? Where I can achieve sonic area in, say I am having say for example I am having a duct like this. Okay, this is my converging diverging duct. Okay, sonic area will be always at the minimum area or not? This thing I have discussed in the last class. Can you recapitulate?
Yes, sir. Yes, sir.
Okay, this is the minimum area. Here that is my throat. Okay, if I am having a converging nozzle, this is the minimum area section. Here that this will be the A star. Okay, so this area here, this will be my A star. Here this will be my A star. Okay, so this is basically the thing. So this is actually at the where
Okay,
in
sir.
a convergent divergent duct where I can achieve the Mach number is equals to 1, or it may not be 1 always. That discussion also we have done in the last class. But if it is 1, that will be obviously at the throat. So that area is basically the sonic area, throat area. Often in the problem you will find out the throat area. That means you have to find out the A star. Is that clear to everyone?
Yes, sir. Yes, sir.
Okay.
Certainly.
Okay. Okay. This one. So up to this we have discussed that this is basically the importance of the star. Now U, and at the throat what will be the density? That will be my rho star. So everything at the throat, the properties will be denoted by the star. Okay. So U is equals to m into under root gamma t. I am not repeating, you know this equation. Okay, m is equals to u by c. C is nothing but under root gamma t for the isentropic flow. So here what will be U star? U star will be obviously m is equals to 1. When Mach number is equals to 1, that velocity is nothing but U star. So under root gamma t star. Here gamma is the constant. Here temperature I will write in terms of T star, not T. Okay, you can see the change in these two equations. So here just if I put this U star by U, can I not write this equation like this? A by A star is equals to rho star by rho, just I am keeping as it is. U star by U means you just take the ratio of these two. U star by U, then obviously you will get this 1 by m will be there. Okay, because U star by U I am doing. So on the denominator I will be having m, the Mach number, and here gamma r will cancel out. So under root T star by T. Okay, that is very simple. So under root T star by T, outside the root I am having 1 by m. Okay. Next we know that this was the equation we have derived for which case? For stagnation, right? For stagnation we have derived T0 was the stagnation temperature, if you recapitulate. So T0 by T is equals to 1 plus gamma minus 1 by 2 into m square. This was the expression we have derived this. We know this equation. Now if I just similarly want to write that T0 by T star, T is any temperature. Here this T is any temperature. T0 is obviously fixed when my velocity is coming to 0. That's why that is my stagnation, your temperature. That concept is separate, T0. But this T, if I try to think, if I want to apply this equation at the throat, then obviously this equation will be T0 by T star or not? Answer me. If I want to apply this equation into throat area, then this ratio left hand side I should write T0 by T star or not?
Yes, sir.
Okay. So this T star, when I'm writing, obviously my Mach number is equals to 1. When my Mach number is equals to 1, I'm just simplifying this and I'm getting gamma plus 1 by 2. So this expression I am getting T0 by T star. What I need? I need T star by T star by T. So can I get T star by T from here? From these two equations? How can I get T star by T? Just I have to
Sir,
divide.
we just ratio.
Yeah, Just I have to divide. If you see, I have to divide this first one divided by the second one. So I'll get T star by this expression I am getting. So I basically I'm converting all these terms. Okay, rho star by rho also will convert. So everything here you see in the T star by T, whatever the expression I have got here, only the M is there, only the Mach number is there. Gamma is basically fixed. Okay, fixed value. So only Mach number is involved over here. Next, if I want to convert this rho star by rho, I have to use this equation, this relation basically. This is valid for your any adiabatic flow. Okay, here my reversible adiabatic flow I am having. For any adiabatic flow, it is true that T1 by rho to the power gamma minus 1 is equals to T2 by rho 2 to the power gamma minus 1. Okay, so here I am just applying T by rho to the power gamma minus 1 is equals to T star by rho star. Okay, just the sonic condition I have applied on the right hand side. So from this ratio, from this expression, I am getting this ratio also. That means rho star by rho. This rho star by rho, I am just simplifying and I am getting T star by T to the power. This power will be inverted obviously because it is in terms of rho over here, but I am just taking that term in terms of T. So 1 by gamma minus 1. So now if I put, you see here T star by T, now is this rho star by rho, if I put in terms of T star by T, already T star by T is there. So half plus this term, half is for this root and half plus actually 1 by gamma minus 1. Just sum up this power and you will get something like this in the power half of gamma plus 1 by gamma minus 1. Okay, and 1 by m is as it is. Now you just replace this T star by T term over here and finally you will get this equation. Just means this equation I am just replacing T star by T over here to the power gamma plus 1 by 2 into gamma minus 1 into 1 by m. This is basically the relation between your A by A star. Okay, A by A star, and here if I know the Mach number, okay, I can easily find out. And if I know the throat area, say, or if some condition is given at any particular area, I can find out the throat area or the vice versa. Okay, so this derivation is clear. The sonic states, how to correlate.
Yes, yes, sir.
Okay, so different terms I can correlate. Okay, practice this. I will suggest you the last derivation and this derivation. These are very small derivations. There is no such big deal. Okay, for this, but you have to just apply uh, the different equations that you know earlier. Okay, for isentropic flow. So this is all about the sonic states of any particular system. System means any particular isentropic flow. And this is always, again I am repeating the last time, that the A star is the throat area. Okay, this thing you may have to find out for a different your problems. It will be asked to solve. Okay, next we are now will be entering to the flow through a steam nozzle. Say for example, this is a nozzle. This is a converging diverging nozzle. Okay, this is a convergent divergent nozzle. You can see this is the inlet, this is the throat. You can see this is my P star, it is denoted by P star, and this is the outlet, this is denoted by 1. Okay, so here my velocity is V0, here my velocity is V1. V1 value is very very high compared to V0, as it is a nozzle. Whenever I am writing nozzle means the outlet velocity is will be much higher compared to the inlet velocity. So for our mathematical purpose, in several steps we may have to use the assumption that V0 is negligible. Okay, we may neglect this V0 because this value of V1 is very very high compared to this V0. Okay, and corresponding the pressure terms are also there. You can see that. And if I want to draw the HS plot of this, it will be something like this. This is the expansion. Okay, actually this is basically due to the pressure drop. Velocity is increasing due to the pressure drop. So if this is the pressure, okay, at the inlet pressure line, constant pressure line, and if this is the outlet pressure, okay, line, so the pressure is dropping. Okay, so here you in the next topic, basically either if possible in the next class, I'll show you about the turbines, steam turbines, where we will enter. Basically, if you when you have studied the vapor power cycle, you have seen that there is a huge drop in this part you called as a turbine, right? And we are getting some work. But basically, this pressure drop or this expansion of the steam is happening where? The turbine blade or in the nozzle. Turbine blades will be placed after this. Okay, try to correlate. I am repeating. Here I am fixing some nozzle. So from the large reservoir, I am giving the input to this nozzle, the hot steam, and the velocity of steam is increased with the help of this nozzle. That is the function of nozzle to increase the velocity. And with this increased velocity, this steam, hot steam, is hitting the turbine blades. After this, okay. So and then that turbine rotates, and we are getting some mechanical work from that. Okay, is that clear? This thing should be clear
Sir.
to you because okay, so
Clear.
because that is a very basic concept, but actually this pressure drop, this is the boiler pressure, this is the condenser pressure. If you just think for a minute, this is the boiler pressure, this is the condenser pressure. So where the pressure drop is happening, the pressure drop is not happening exactly in the turbine blades. Very small pressure drop happens in the turbine blade. Some cases it is negligible, but the main pressure drop is happening in the nozzle that is situated just before the turbine blades. This point is clear to all of you.
Yes, sir.
Clear,
Okay,
sir.
sir.
Clear.
So basically now you can see this dotted line is nothing but the throat area. Okay, so this is the sonic conditions are will be applied for this dotted line, that is the star. This is the throat basically, and again it is expanding, and finally this is the one. Yes, this is the outlet from the nozzle. So if I just let us consider the same thing, we'll apply the energy equation over here now. So let us consider the steam flow through a convergent divergent nozzle. If the flow is adiabatic, then the heat transfer and work transfer will be zero. Okay, because from the nozzle we are not getting any work. If you see from the nozzle we are not getting any work. From the turbine we may get work. So nozzle and turbine is basically not a separate thing. Basically, why we always write here just by drawing a vertical line and we are writing WT from here, that is basically the turbine work. Okay, but if I just consider this nozzle and turbine comes in a same casing, I told you initially. So basically this from this nozzle we are not getting any positive work, from the turbine we are getting. uh, so as and we are also considering that is this nozzle is my insulated, so there is no heat transfer also, that is negligible. And neglecting potential and kinetic energy changes, we can write this one, that means H naught, that means very simple SFE, steady flow energy equation, H naught, okay, that is at the inlet, plus V0 square by 2 or V naught square by 2 is equals to H1 plus V1 square by 2. As I told that from the nozzle at the outlet velocity is very high compared to the inlet velocity, so we can neglect this inlet velocity V0. Okay, so if we neglect this, we will get the expression of V1, okay, in terms of enthalpy. So if I neglect, if you just you can see here we are simplifying this H naught minus H1. H naught is obviously higher, H1 is lesser. So H naught minus H1 into 10 to the power 3 is basically this H, the small h, whatever you will take these values either from steam table or from your Mollier chart. These units will be in terms of kilojoules per kg Kelvin. Okay, but if you want to calculate this velocity in terms of meter per second, you have to convert that kilojoules to joules. That's why this your 10 to the power 3 is multiplied over here. Okay, you can see in our books also 10 to the power 3 is multiplied, but the reason is that one. Okay, we have to convert that kilojoules to this joules, and ultimately we're getting the velocity in terms of meter per second. Okay, and this 44 by 72, 44.72, keep it in your mind because this equation may have to use several times in any problem. Okay, so basically this 1000 and this 2, that means 2000, if you just root it, you will get something like this 44.7. So this is the equation v1 is equals to, in this term, this much of meter per second. So now we will just proceed that same thing, but for the isentropic flow, we have to apply that condition also, as we have considered the isentropic flow through this nozzle. So TdS is equals to dH minus VdP, and ds is also 0 over here because it is my isentropic flow. So reversible adiabatic flow. So ds term is my 0. So dH is nothing but is equals to your VdP. Okay, and if we integrate this from 0 to 1 means from inlet to outlet. If I integrate from 0 to 1, that means from inlet to outlet. Just I'm just keeping the integration sign, and then we can write this H naught minus H1. This should be H1 minus H naught, but as we are writing H naught minus H1, we are keeping a minus over here. Okay, VdP this term. So this H naught minus H1 is what? This is nothing but V1 square minus V0 square by 2, isn't it? Just refer the equation in the last slide. Okay, H naught plus V0 square by 2 is equals to H1 plus V1 square by 2. Just from that equation, we are writing this. Again, we can neglect this V0 here also. That is not a big deal. But we can write the equation like this. Next is the process, as it is a adiabatic process, P v to the power k. Here we are taking k. You can take gamma also. You can, it may be k, it may be n, whatever. Different books follow different notations. So P v to the power k is equals to constant. This is the thermodynamic equation of that particular process. So here we will apply this. Here V naught square I am obviously neglecting. So I am writing V1 square by 2 in the left hand side. You can see that. Here some steps I will skip. You have to just do it by own, but I will show you the final equation. Obviously, this is nothing but the mathematical way to find out. I am showing you the steps. V1 square by 2 is equals to will be what? Integration V dp, you can see. Okay, now V dp, basically this V dp, this V, just I am writing, just I am using this equation. How I am using? This P v to the power k is equals to constant. So if this is at any position, if this P and V, P is the spatial and small v is the specific volume. Okay, don't mix up with small v and capital V. Capital V is the velocity, small v is the specific volume. So if this P and this small v is the pressure and specific volume at any position, I can write this equation as P v to the power k is equals to P0 V0 to the power k, because P0 and V0 is at the inlet condition. So I can write this by analogy. So P v to the power k is equals to P0 V0 to the power k. From that we are writing this. From that we are taking this V only. If you take out from that to your equation, whatever I told right now, P v to the power k is equals to P0 V0 to the power k. From that, if you take out this V, you will get this expression. Okay, you will get this expression, and you have to integrate now. And always remember, this P0 V0 is constant. These are not variable. You cannot integrate this P0 V0. P0 V0 is fixed at the inlet. P is variable and V is variable. But we have, as we are having dP, so we have converted this V into P, pressure term. So here also at the outlet also you can use the same thing. That means P0 V0 to the k is equals to P1 V1 to the power k. I can write this. Okay, because 0 is at the inlet, 1 is at the outlet. One state is at the outlet. So here we will obviously, here this step I have skipped. You have to do it by own. You just check it. I have checked it that I have got this expression directly. Directly means after 3-4 steps you will get this one. You will obviously not get this one in your book also. Okay, you have to do it by own. I have done it, then only I am saying it, yes, it is coming. Okay, so just by this you converse, just this your converse things, that means this just you have to convert many a times. P0 V0 to the power k, P1 V1 to the power k, and you have to integrate this P to the power minus 1 by k. Okay, basically you have to just your integrate that, and after putting the limits you will get this expression, simplified this equation, that k by k minus 1 P0 V0 minus of P1 V1. Okay, so this thing you try at your home. You just this step in between 3-4 steps are there. So, and if I replace this, you can see if I take common P0 V0 outside, I am getting something like this, 1 minus of P1 by P0 to the power k minus 1 by k. So from this, okay, I'm again rewriting this equation on the next slide. This same equation, this last equation, whatever I have got. So I have got this equation. Okay, finally that was V1 square by 2. Basically that just I am writing V1. From that I am writing V1. V1 is the outlet velocity that I need, outlet velocity from the nozzle. So this is the expression. Okay, to the power half, because it was V1 square, so whole thing to the power half will be there. Now if I want to calculate the mass flow rate, once I have got the velocity, I can obviously calculate the mass flow rate. Very important equation. Omega is equals to A1 V1 by small v1. Okay, in steady flow energy equation also you have used this equation. Same equation will be used over here also. The basic equation is same. Omega is the mass flow rate, A1 is the area at the outlet, V1 is the velocity at the outlet, small v1 is the specific volume at the outlet. So A1 will be as it is, and we are keeping this V1 like this, the expression I have got right now. So this is the term that I have got, and this small V1 we have taken inside. That's why you can see over here V1 square is there once. Okay, one V1 square is there. That means this V1 we have taken inside. So if I simplify this omega by A1, okay, omega by A1, that means mass flow rate per unit area. This is what mass flow rate per unit area. So this is nothing but, again, some mathematical simplification is there, P0 by V0, okay, and we are getting something like this inside. And by analogy, you can see this is my omega by A1, okay. If I write omega by A1 is the outlet area, obviously. If I want to calculate this ratio, this mass flow rate, basically if I want to calculate this mass flow rate or this area at any area, okay, at any section of the duct, obviously which thing will be changed in this equation on the right hand side? Whatever the suffix 1 you are having, that will be omitted only. That will be omitted only. P0 V0 will be not changed. Okay, I repeat, P0 V0 is the inlet conditions, those will be not changing. Only here in place of A1 I have written A, okay, any area. So that's why there at the area A, at the section A, obviously the pressure will be P, for example. Okay, so only that thing is changed, other parts have not been changed, if you see. Okay, so now you see this equation, if you see properly, this mass flow rate is dependent on what? You see, for a given value of stagnation pressure and volume, the mass flow rate will be only depend on the pressure ratio. That means, again, I'm repeating this. For a given value of stagnation pressure and volume, the inlet condition is called stagnation. And we also know that suffix 0 means stagnation. And here we are also calling this inlet condition as the stagnation. Why? Anyone can tell me? Have you understood my question? Have you understood my question? These things will be not answered by your book. Okay, these things will be not answered by your book, whatever book you are having. Here, suddenly in the book, you can see it is written for a given value of stagnation pressure and volume, the mass flow rate will depend on such things, whatever. But for a given value of stagnation pressure means P0, stagnation volume means specific volume means V0. But from the initial point of time, I have several times I have told 0 stands for the inlet condition. So how the stagnation term and the inlet term mix, or just we are considering as same? What is the physical or practical reason behind that?
Sir, because we assume that the velocity is almost negligible at inlet.
Okay, velocity is only negligible at inlet. Yes, you are a bit correct, because we have told several times this thing also. We are neglecting the inlet velocity, but that I told in the respect of that outlet velocity is very high, so we are considering that inlet velocity is negligible. But if there is some value of inlet velocity. Basically, the physical reason, you can say, if anyone asks this, you can say it like that: that whatever the inlet of this stream flow, that is basically coming from a large reservoir. That is basically coming from a large reservoir. So that in the large reservoir, whatever the steam we are storing, we are keeping that steam. So there is no velocity. So that is basically at the state where we can consider that it is my stagnation state. That means my velocity is 0. Okay, we can consider that. Not exactly it is, but we can consider as a stagnation state at the inlet condition. So that's why inlet condition is always pre-assumed as the stagnation pressure and volume. In several times you can see in your book. Is that clear? This point?
Yes, sir. Yes, sir.
Okay.
So
So
just
this,
like a reservoir, it acts like a
yeah,
reservoir
yes,
that it
yes.
will
It
not
acts
change.
like a reservoir. Just we are considering it is coming. The flow is coming from a large reservoir where I am storing the fluid, and then we are feeding that to the nozzle. So that is the concept. So here, what is written over here, that inlet conditions, if these are fixed, obviously these will be fixed. It is dependent on what? It is dependent on the pressure ratio. It is depend. You can see the P by P0. It is only dependent only this term, because P0 V0 is constant, K is constant. So this term P by P0, because this, if this P is varying, this P0, this P by P0 term will also vary. So this mass flow rate will depend on this ratio. So if I can find out the optimum value of this ratio P by P0, or I should say the maximum value of this your ratio, then obviously we can find out the maximum value of this mass flow rate. That is my goal, to find out the maximum flow rate of the steam through the steam nozzle. So I have to just differentiate this equation. I have to differentiate with respect to what? With respect to this ratio. Which ratio? P by P0. Because it is wholly dependent on P by P0, no other terms. You can see that from this equation. So D of P by P0, only this term, because rest of the term, this term is your constant, and the power also you can neglect, because those terms will be getting uh, not relevant. It is depend on only inside this second bracket, whatever you are having, it is only dependent on this, the maximum value of this ratio. So I need some optimum value of this P by P0, this ratio. Okay, so this you can see here. If I just differentiate this, I'll get something. I'm not going to in details, because these are very simple derivation, just your differentiation with respect to P by P0, taking the powers and all, and ultimately we are getting this final expression, which is my P star by P0. This P star is called critical pressure. Okay, this P star by P0, right? So P star by P0, this ratio is known as your critical pressure ratio. Okay, certain pressure ratio, here it is written, at a certain pressure ratio it will be maximum. It will be maximum means this mass flow rate through the steam will be maximum. What is that ratio? We have got just by differentiation, that P star by P0. That means now this is the P by P0. This ratio is your 2 by K plus 1 to the power K by K minus 1. Very important. You may have to use this equation in your several problems. So if we put this equation over here, I will get the maximum value of discharge. Is that clear up to this?
Yes, sir.
Okay.
Yes, sir.
So this derivation, it may be asked. This derivation is a bit long if you see compared to the others earlier, but this derivation often comes in your semester exam also. Okay, you have to derive the expression of critical pressure ratio. This in the question, this K may be N. Okay, whatever the this exponent may be, but this ratio, this concept will be same like this. Okay. So on the next class, we will finish up the nozzle part, and we will also show you one problem. Okay, on the next class I will show you some this nozzle, your efficiency, and this some physical this nozzle area part, because this will be used for your problem solving, and then obviously we will solve one particular problem. Okay, any doubt after this? So all of you have given the attendance, right?
Yes, sir.
Yes,
Okay. So if I am getting tomorrow's class, tomorrow you can think that we can finish the nozzle and with a problem. Then we will enter to the exactly to the steam turbine blending part. That means the impulse turbine and your reaction turbines and your turbine compounding. That will take 1 month. Okay, 4 to 5 classes that will at least need. So then, because this nozzle part is also very important. Whatever these things we have discussed today, several problems you can see in your group. Okay, try to practice those problems from now, so that in the next class you will understand the problem that I will discuss also. Okay, thank you. Then,
Yes, sir. Thank you.
okay, thank you for attending.
thank you, sir.
See you in the next class. Okay.
Bye.